Okay, here are our solutions for series and parallel circuits. So for this part of the worksheet, what we're going to do is calculate the equivalent resistance, the current flowing through each resistor, and the power dissipated by each resistor. So and how it's going to work is the same kind of circuit is going to be on this same page. So looking at this page, these are all series circuits. And they're all series circuit because there is only one path for the current to flow through. And if we kind of look at this in terms of Kirchhoff's rules, one of those rules being current in equals current out, which means what's most important as we think about that, especially for series circuits, is that resistors don't use up current. That's a really, really important thing here as we think about circuits. Resistors don't use up current because one of our big rules here is current in is equal to current out. I guess I'm going to spend a little bit more time talking about this than I thought. And this is a consequence of conservation of charge. Conservation of charge is, outside of a nuclear reaction, we cannot create or destroy charges. Overall conservation of charges, we can't create or destroy net charges, right? We can't create unequal charge. But outside of a nuclear type reaction where we have beta decay or something like that, we can't create charge. And certainly a circuit is not going to be something that's going to create or use up charge. And current is closely related to charge. So one of our fundamental conservation laws in nature is that we're not creating current. Resistors are not things that are going to destroy current. They're not going to destroy charge. So that's why they're kind of tied together. That's what tells me that inside of a series circuit, current total is equal to current 1, is equal to current 2, is equal to current 3. Because the current that we have coming into a resistor has to be the same as the current that we have coming out of a resistor. Now, for series, and sort of our other rule is that in a loop the voltage does get used up. Total voltage is voltage 1 plus voltage 2 plus voltage 3. And total resistance is resistance 1 plus resistance 2 plus resistance 3. That's how we do things in series. So let's do that for each one of these. All right. We'll just do each one at a time. So looking at this, I have 4 ohms and 4 ohms. So the equivalent resistance, the total resistance here, is 8 ohms. Now, if I want the total current, the only way to calculate the total current is to use the total voltage and divide it by the total resistance. That's the only way to calculate. We have to use total numbers here. So the total voltage is 8 volts. The total resistance is 8 ohms. So here we have 1 amp. That's our total current. So that means there's 1 amp through here and 1 amp through here. Because we're in a series circuit, and in series the current is the same all the way through. So if I want to look at this individual resistor, the voltage on the 4 ohm resistor is equal to the resistance of the 4 ohm resistor times the current through the 4 ohm resistor. So the voltage on that 4 ohm resistor is 4 ohms times 1 amp of current, or 4 volts. So this 4 ohm resistor has 4 volts dropped across it. This 4 ohm resistor, that's identical. It also has 4 volts dropped across it. And that makes sense because those add up to the total voltage. And if I want the power for each one of those, power is IV, current times voltage. So we have 1 amp times 4 volts. So that power on each one is 4 watts. And 4 watts. That's that one. So I'm going to erase, I'll leave it there. So for this one, the next one, the total resistance is 5 ohms plus 5 ohms. We can do that in our heads. That's 10 ohms because we're just adding them together to get the total resistance. And so the total current is the total voltage, 20 volts, over 10 ohms. Total current is 2 amps. That means there's 2 amps going through this one and 2 amps going through this one because, again, total current is the same all the way through. And so if I want an individual voltage, the voltage on one of those 5 ohm resistors is the current through the 5 ohm resistor times the resistance of the 5 ohm resistor. So that's 2 amps times 5 ohms. The voltage on that 5 ohm resistor is 10 volts. So we have 10 volts dropped here and 10 volts dropped here. Power, running out of space, power is current times voltage. So we have 2 amps times 10 volts. So that power is 20 watts. And that's on each one of those. So here we are solving those individual circuits as we go. Let's look at C. We'll zoom in so we have a little bit more room to write. So for this one, our total is going to be 4 ohms plus 8 ohms because we're just adding them together. So that's 12 ohms. So if I want the total current, I can get that now. That's the total voltage over the total resistance. So that's 16 volts divided by 12 ohms. So the total current comes out to be, what do we have? 4 over 3? 4/3? Yeah. 1.33 amps. That's my total current. That means I have 1.33 amps moving through this resistor and 1.33 amps moving through this resistor, because our rule here is that they have to have the same current going through them because current is not used up. So for this one, the voltage for the 4 ohm resistor is going to be 4 ohms times the current running through it, 1.33 amps. So the voltage for the 4 ohm resistor comes out to be 5.32 volts, or really close to it. And if I want the power here, power is current times voltage, so that power is going to be 1.33 times 5.32, or 7.07 watts. For the 8 ohm resistor up here, the voltage across the 8 ohm resistor is the current through it, 1.33 amps, times the resistance, 8 ohms. So the voltage across the 8 ohm resistor is about 10.64 volts. If you put those together, you get something very close to 16. I think it's a rounding error if you don't quite get that. So that's our voltage, and if we want the power across this, it's going to be the current times the voltage, so 1.33 times 10.64, and the power on that one comes out to be 14.15 watts. So hopefully we're looking at this and we're seeing this as a pretty repeatable process. Let's move on to our next one. For our next one, we have 3 resistors this time, but that's okay because the total resistance is still all those things just added together. So it's 2 ohms plus 4 ohms plus 6 ohms. So our total resistance comes out to be 12 ohms. That's our total resistance. Now that we have the total resistance, we can find the total current. So the total current is going to be the total voltage, 20 volts, divided by the total resistance, 12 ohms. So the total current comes out to be 1.66 amps. And because this is a series circuit, that means the current through each one of these is 1.66 amps. Because in series, we know that the total current is equal to the individual current moving through any resistor. Because it's current in, 1.66 amps in is current out, 1.66 amps is current in, 1.66 is current out, 1.66. Because current does not get used up in a series circuit. So looking at this one, the voltage is the voltage on the 2 ohm resistor is the current through the 2 ohm resistor, 1.66 amps times 2 ohms. So the voltage here is 3.33 volts. And power is the current, 1.66 amps, times the voltage, 3.33 volts, ends up being 5.53 watts. For the next one, the voltage is 1.66 amps, the current through the resistor, times the resistance of 4 ohms. So that voltage comes out to be 6.64 through this resistor. And then the power through that resistor is 1.66 amps, the current times the voltage, 6.64 volts. And that comes out to be 11.02 watts. And then for the last one, the voltage here is the current, 1.66 amps, times the resistance, 6 ohms. And we end up with a voltage of 9.96 volts, or really close to 10 volts. And the power here is the current, 1.66 times 9.96. Power is 16.53 watts. Same process over and over and over again, no matter how many resistors we have, which is good. This thing's about to get crazy. Here we have 4 resistors, but again, to find the total resistance, and we'll do it over here to give ourselves a little bit of room. The total resistance is just resistor 1, 2 ohms, plus resistor 2, plus resistor 3, plus resistor 4. So that total resistance comes out to be 8 ohms, and the total current comes out to be 32 volts, the total voltage divided by 8 ohms, the total resistance, giving me 4 amps. That means we have 4 amps through each resistor, because current does not get used up. It's the same all the way through. So we have 4 amps through each resistor. Now, since they're all the same, it's going to make this a little bit easier. The voltage through one of those 2 ohm resistors is the current through the 2 ohm resistor times the resistance of the 2 ohm resistor. So 4 amps times 2 ohms, that gives me 8 volts. That means each one of these things has 8 volts dropped across it, because they're identical, which makes sense because 8 plus 8 plus 8 is 32. That's what we want. And then if we get the power is IV. So we have 4 amps times 8 volts through the individual resistor, and so that power comes out to be 32 watts. And that's what's going to be dropped on each one. You can find the total power by adding that together. Very last one. We have 5 this time, which seems like a lot. So the total resistance here is R1, 3 ohms, plus R2, 3 ohms, plus R3, 4 ohms, 4 ohms, plus 8 ohms. So the total resistance is those things added together. So our total resistance comes out to be 6 plus 16, 22 ohms. Total resistance. Our total voltage is 44 volts because it tells us that there, and that makes our total current, the total voltage, 44 volts divided by 22 ohms. Again, to get the total current, you have to use total voltage and total resistance. My total current comes out to be 2 amps. That means through each one of these, we have 2 amps. So to get the voltage on an individual one, it's current times resistance in that individual thing. So 2 amps times 3 ohms, that tells me I have 6 volts dropped across this. 3 amps times 2 ohms, Tells me I have 6 volts dropped across this one. 4 ohms times 2 amps is 8 volts. 4 ohms times 2 amps is 8 volts. 2 amps times 8 ohms is 16 volts. All we did was V equals IR for an individual resistor. For an individual resistor, use the individual resistance and the individual current. And in most cases, you can only do the individual current once you find the total current. Now that we have all of those, we can also find the power. Power is current times voltage, so 6 volts times 2 amps gives me a power of 12 watts. 6 volts times 2 amps is 12 watts. 8 volts times 2 amps is 16 watts. 8 volts times 2 amps is 16 watts for power. And 16 volts times 2 amps is 32 watts of power. That's how we would find the individual power there. Okay, that's everything for the series part of this worksheet. Let's move on to the next part and see what we've got. Okay, we've got some more practice problems. So we have 3 6-ohm resistors connected in series to a 54-volt battery. If it's series, then we have this 54-volt battery, and it's connected to 1 series resistor, that's 6 ohms, 2 6 ohms, and 3 of them that are 6 ohms. And so they're all together, all in a row. Because it's series, that means we have one path for the current. There are no choices. Calculate the current passing through each resistor. Because this is series, we'll write this down. In a series circuit, the total current equals the individual currents we're going to find the total current first. That's how we have to do this. We have to find the total current first. In order to find the total current, we're going to take the total voltage and divide it by the total resistance. We need the total resistance. Because we're in series, it's R1 plus R2 plus R3. So 6 ohms plus 6 ohms plus 6 ohms. We get 18 ohms. So if I want the total current, it's going to be 54 volts divided by 18 ohms. So the total current comes out to be 3 amps. And because that's the same as the individual resistance, the current through each one of these is going to be 3 amps. 3 amps through each resistor because it's series and it stays the same the whole time. Calculate the power dissipated by each resistor. Okay, so power is usually current times voltage, but I don't know the individual voltage here. So what we're going to do is make a substitution. We know that voltage is also current times resistance. And so what we can do is plug that in for voltage. So power is equal to current times the resistance. All we did was make a substitution. And so the power is I squared times R. So that power is the 3 amps through an individual resistor squared times the resistance of an individual resistor, 6 ohms. And so we get 54 watts. And since they're all identical, that's the power dissipated by each resistor. Now we have these circuits to deal with. If we look at these, what we see is a branch. That branch tells us that we have a parallel circuit. So for this parallel circuit, what we're going to do, what we're going to say is that at this branch, current in equals current out. Same idea. It's the same sort of thing that we used before, but at one of these branches, we have one current in and two currents out. Or if we want to say it a different way, the total current when it splits is the current 1 plus current 2. Again, current's not being used up, it just, the current splits at a junction. If there are no junctions, the current stays the same. If there are junctions, like we have here, places where wires come together, the current's going to split. Because the current splits, well, because each of these are attached to the battery in the same way, we have to go down to 20 volts. That tells us that the total voltage is voltage 1 plus, no, I'm sorry. The total voltage is the same as the individual voltage when we're in parallel. And then because of some weird rules, that gives us a different way to add up resistors. 1 over total resistance is 1 over R1 plus 1 over R2. They add kind of upside down. So we're going to have to use the calculator to do these. No problem, we have calculators. So those are our rules for parallel circuits. And they're parallel because we see all of those junctions. Now, let's talk about this first one. Our process is going to be the same. We're going to go ahead and find the overall resistance first. So here, 1 over the total resistance is 1 over 4 ohms plus 1 over 4 ohms. And so if we pop up the calculator for that, okay, so 1 divided by 4 plus 1 divided by 4 is equal to 0.5. That means 1 over R total is equal to 0.5. And so I have to take the inverse of that to get R total. So R total is 2 ohms. We know that now. Now if we look at these individual resistors, I know that the total current is 8 volts. So that means I've got 8 volts on this 4 ohm resistor and 8 volts on that 4 ohm resistor, because the total current is the same as the individual currents. Each single resistor, when we're in parallel, uses up all of the voltage. Voltage is what gets used up. So they each have to use up that 8 volts of current. I know that current is equal to voltage divided by resistance. So here, for this individual resistor, it's going to be 8 volts divided by 4 ohms, or 2 amps. 8 volts divided by 4 ohms, that's also 2 amps. And then if I want the power, it's current times voltage. So 8 volts times 2 amps gives me 16 watts of power. 8 volts times 2 amps gives me 16 watts of power. So we're going to repeat that process for all of these. Let's come over here. So we have 2 resistors here. 1 over R total is 1 over 5 plus 1 over 5. So you put that into your calculator, and 1 over R total ends up being, I guess I'll just do the calculator for you. That's fine. 1 divided by 5 plus 1 divided by 5 equals 0.4. So 1 over R total is 0.4. If I want R total, we take the inverse of that. That's the x to the negative 1 button. Ends up with 2.5 being R total. So R total comes out to be 2.5 ohms. That's our equivalent resistance. Looking at this, we see that it's 20 volts total. So each individual voltage is 20 volts. And if I want to find the current That's the voltage divided by the resistance. And so here it's 20 volts divided by 5 ohms. That's a current of 4 amps. 20 volts divided by 5 ohms, current of 4 amps. And then if I want the power, it's current times voltage. So 4 amps times 20 volts. That's 80 watts. 4 amps times 20 volts. 80 watts dropped across each one in this case. Going on to the next one. Now here they're not the same anymore, but our process still is the same. 1 over R total is 1 over 3 plus 1 over 6. So with the calculator, 1 divided by 3 plus 1 divided by 6. Nope, that was another 3. 1 divided by 6 gives me 0.5. So 1 over R total is 0.5. Take the inverse of both sides, so 1 divided by that. We get R total is equal to 2 ohms. That's our equivalent, or our total resistance. Then over here, because it's 12 volts total, I have 12 volts dropped across each resistor. So if I want the total current I know is voltage divided by resistance. So 12 volts divided by 3 ohms is 4 amps. And then 12 volts divided by 6 ohms is 2 amps. And then if I want the power is current times voltage. So 4 amps times 12 volts is 48 watts for that top one. And 2 amps times 12 volts is 24 watts for the bottom one. Part D, again, they're not the same. So if I want the total resistance, 1 over R total is 1 over 30 plus 1 over 20. That makes 1 over R total equal to, and your calculator, because this is how I really want you to do it, 1 divided by 30 plus 1 divided by 20, divided by 20 is that number. So 0.0833. That makes R total equal to the inverse of that. So we do x negative 1 for that number, and it's 12. So R total is 12 ohms. There we go. Now, because it is 100 volts up here, that means across each resistor we drop 100 volts because they're in parallel, and in parallel the voltages are the same. So to get the current is equal to the voltage divided by the resistance. And so that's 100 volts divided by 30 ohms. It's not a pretty number, but we get 3.33 amps. And then 100 volts divided by 20 ohms is 5 amps. And then if I want the power is current times voltage. So 3.33 amps times 100 volts gives me a power of 333 watts. That's a lot of power. And then 5 amps times 100 volts is 500 watts. And if you're noticing a pattern, it's that with the same voltage, a smaller resistor, with the same voltage, a smaller resistor has more power. So if you look at a 100-watt bulb versus a 60-watt bulb, a 100-watt bulb has less resistance, more power. Here, it's a different way of drawing things in parallel. They're still in parallel. So we're going to do 1 over R total is 1 over 30 plus 1 over 60. So we got 1 divided by 30 plus 1 divided by 60. And we equals 0.05. So 1 over R total is 0.05. To get the total resistance, we're going to take the inverse of that. Do x negative 1 of 0.05. And that gives me R total as 20 ohms. That's my total resistance. Now, because it's parallel, that means this 12 volts is dropped across each one. So I got 12 volts here, and I got 12 volts here. because it's our rule. That means that makes it a little bit easier. So the current is going to be the voltage over the resistance. So for this first resistor, it's 12 volts over 30 ohms. So this one is we'll say 0.4 amps. And for this one, it's 12 volts divided by 60 ohms, 0.2 amps. And then if I want the power is current times voltage, so 0.4 amps times 12 volts, 4.8 watts, and then 0.2 amps times 12 volts is 2.4 watts. All right, last one. These are still in parallel because we have the choice to go through any one of these resistors. So because it's in parallel, 1 over our total is 1 over 2 plus 1 over 4 plus 1 over 4. So in our calculator, we can just do all of that. 1 divided by 2 plus 1 divided by 4 plus 1 divided by 4. That gives me 1. Well, that makes it easy. So 1 over our total is 1. When you take the inverse, that tells you that our total is equal to 1 ohm. Here, because we're in series, it's 12 volts dropped across each one. So we have 2 ohms and 12 volts, 4 ohms and 12 volts, 4 ohms and 12 volts. Because in parallel, the total voltage is equal to the individual voltage. If we want to find the current is the voltage over the resistance. So for the top one, it's 12 volts over 2 ohms. So we have 6 amps going through here. For the next one, it's 12 volts over 4 ohms. So we have 3 amps going through here. And the last one, it's 12 volts over 4 ohms. So again, we have 3 amps going through here. That's backwards. Remember that current goes in the direction of positive flow. So that's the direction of all the currents. Now, if I want to find the power is current times voltage. So it's going to be 6 amps times 12 volts. So we have 72 watts up here. And then it's going to be 3 amps times 12 volts. So we have 36 watts up here. 3 amps times 12 volts, 36 watts down here. Those are our parallel circuits. And because why not, there is still some more to go. So let's move on. 3 9-ohm resistors are connected in parallel and then connected to a 12-volt battery. So we got a 12-volt battery, and it's got 3 9-ohm resistors, but they're in parallel. So here's one of my 9-ohm resistors. Here's one of my 9-ohm resistors. And here's one of my 9-ohm resistors. It's parallel because I have parallel paths for the current to flow down. It has a choice and go through all of them. Calculate the current passing through each resistor. Because they're in parallel, it's 12 volts being dropped across each one. If we want to think of it in terms of loops, one of our loops could be here, to where all of the voltage is used up in that resistor. Another loop, get rid of the wire, would be here, and notice that they are independent of each other. All 12 volts would be used up in that loop. And then our last parallel loop would be this one, where all 12 volts are used up in this last parallel loop right here. That's why all 12 volts get used up on each resistor. So if I want an individual current, so a current through a 9-ohm resistor, that's going to be the voltage across that 9-ohm resistor divided by the resistance of that 9-ohm resistor. So 12 volts divided by 9 ohms gives me 1.33 amps through each resistor. So each resistor gives me 1.33 amps running through it. And then calculate the power dissipated by each resistor. Same deal. Power is going, well, we can do power is IV now because we have the current and the voltage. So that power is 1.33 amps times 12 volts. gives me 16 watts through each one. And that is our worksheet on series and parallel resistors.